for tuning in today to our Physics Fun channel. We are going to talk a little bit about electromagnetic induction. So electromagnetic induction is going to give us the firm foundation on which we can build our comprehension of other really cool machines like transformers, generators, and motors. So the big picture idea for electromagnetic induction is that in the presence of a magnetic field that is changing, meaning there's a change in flux, there will be an induced current. And if there is, in fact, an induced current, then this induced current will also induce another magnetic field separate from the first one that caused the current in the first place. Now, we call it electromagnetic induction because it's actually really hard to differentiate between electricity and magnetism. And the more that you study physics, the more that you'll see the connections between the two. So it's really hard to talk about one without discussing the other as well. Another big picture idea that we'll cover is this idea of relative motion between a conductor and a magnetic field. And that relative motion is what actually induces the EMF in the conductor, meaning the relative motion is responsible for the change in flux. And just to reiterate, the last big picture idea is that the induced EMF in the conductor induces another magnetic field. And like we already said, this field is different than the original field that induced the EMF to begin with. Okay, so remember back we talked about Hans Christian Ørsted. He was the physics instructor who made his great big discovery during a lecture. And his discovery was that when you have current running through a wire, there will also be a magnetic field. And this he observed by running current through a wire and seeing a compass needle deflect. So when there is current, there's also a magnetic field generated by that current. And just as current can induce a magnetic field can also induce current with those parameters met that we mentioned earlier. So our rule is for a closed circuit and a magnet, if there's relative motion between the two, then a current is created in the circuit. So this is not new. We kind of covered it for the past few days in class, as well as talking about it above in the big picture idea. Relative motion really just means a change in flux. Okay, so the importance of relative motion is that it means there is a change in flux. So flux, I think, has confused people in our discussion because it is so closely related to field, but it's not equal to field. The flux is a product of field, where the strength of the field contributes to the value of the flux, but they are not one and the same. We have a couple of different definitions for flux. When you guys first encountered flux, we defined it as the number of field lines that intersect a cross-sectional area at a right angle. We also defined flux as the field strength as sensed or felt by a nearby conductor. And lastly, we also have a formula for flux that's calculated as the product of the cross-sectional area times the strength of the field times cosine theta, where theta is the angle between the perpendicular or the normal to that cross-sectional area and the field. So you can see that illustrated here in the image, that theta is the angle between the perpendicular to the plane and the magnetic field. So you'll see that when theta is 0, when the field lines actually intersect that cross-sectional area at a right angle, then theta is 0, and you guys know cosine of 0 is 1. So therefore also, when cosine is 90, meaning when the plane is actually moving parallel to the field, then cosine of 90 is 0, and we don't have a flux. Okay, so getting back to how this relates to electromagnetic induction. So you'll see here a few images of magnets, and therefore a magnetic field. and a series of loops which are going to represent our conductor. So in the first image here, we have a magnetic field B indicated by the light blue lines. The conductor are these series of orange rings, and the dark blue arrows are indicating the direction that the magnet is moving. So if the field is caused by a permanent magnet, then the flux the conductor feels can be changed by moving the magnet. Meaning, if you're the conductor, then if I move the magnet closer to you, you will feel the field more strongly. And if I move the magnet away from you, then you will feel the field recede or feel it become less strong. So that's one way that the flux can be changed, by moving the source of the field closer or further from the conductor. In the case of an electromagnet, which you see here on the right, not only can you move the actual magnet closer or further from the conductor, but you can increase the field strength without having to move the magnet at all, which would result in a change in flux. And you know that the way to do that is to insert an iron core into your electromagnet. So if we keep the electromagnet still, but we insert an iron core, then the strength of that field B would get stronger, and then the loops or our conductor would sense a change in the flux. Okay, so we've discussed flux, what it is. We've discussed flux in the sense of how to change it and what a changing flux might look like in an image or picture. But now what do we do with that information? So remember the parameters that we spoke about earlier. We said that if a flux, or if the flux is changing and there is a conductor nearby, then there will be an induced current in that conductor. So here we see a couple of different pictures, and before you get overwhelmed, let's just go through each picture one by one. So starting with image number 1, here we have a changing field indicated in the light blue, and I'm actually telling you that B is changing. So from this picture alone, you wouldn't be able to tell that the field is indeed changing and that the flux is changing. I'm just telling you that. So here B is changing, and a current is therefore induced in the conductor because of the changing flux. So the current is indicated in that dark pink color. So it's showing you that current is now running through the coils. In image number 2, we iterate that the presence of current creates a magnetic field in and around the conductor, and that this field is separate from the original field that caused all of this to happen. So here we see an original field again in light blue, and I've indicated to you that this is a south pole that is moving closer to the conductor. You see the induced current I as indicated in the dark pink, and this time I've drawn in for you in purple the induced magnetic field of the coils. So here you see two separate fields, the light blue field that existed first, and then the purple field, which is a byproduct of the induced current. Now here in image 3, we've got a new factor added in, which is right-hand rule. So in image 3, we say the direction of the induced magnetic field will always oppose the change in flux that caused the induced current. Now before we let that totally confuse us, let's just break that down. So the direction of the purple field, step 3 is saying the direction of the purple field will always orient itself such that it opposes the change of the light blue field. And you'll see a little bit more of an explanation in the practice that's coming up right after this. Image 4, or rather, there is no image, but step 4, the direction of the induced field will determine the direction of the induced current by the right-hand rule. So once we, in step 3, determine the direction of the magnetic field of the coils, that will tell us the direction of the current if we follow right-hand rule. So you can see in image 3, we have a south pole to the left of the coils and a north pole to the right. So if we orient our right hand rule, just like the drawing, then we would see that the current is actually curling over the top of the coils, going straight down the page and winding under the bottom. Now steps 3 and 4 constitute Lenz's law. Lenz's law says that when you have an induced current, the current will always be in such a manner that the magnetic field that accompanies the current will oppose the change that caused it. So it's a little bit of a backward sentence, so that's why I kind of broke it down in the reverse, where in step 3 we said the magnetic field, right, the induced magnetic field will always oppose the change in flux that caused the current. Then we talk about the direction of current. Now let's do a little bit of practice to see if we understand what these steps or what these rules really mean for us. Okay, starting with practice, these aren't numbered, but number 1, meaning to the left. Here we see an existing field in light blue. This is a north pole that moves closer to a conductor. Okay, so if it's a north pole getting stronger, then by Lenz's law, which says that the direction of the induced magnetic field, so the direction of the purple field lines, will oppose the change of the light blue field lines. So if the purple lines are going to oppose the change of the light blue lines, then the purple lines will also need to have a north pole on the left side of the coil so that it can oppose the approaching north pole. So like charges repel, as do like poles. So a north pole's getting close and you want to oppose that, then you're going to also put a north pole facing that direction, facing the approaching north pole, so that they would repel each other. Now you can see here, if I align my thumb to the left of the coils using right hand rule, then the current would run from the bottom of the wires up and over the top. Okay, so it's the reverse of the picture of right hand rule that you see above. We orient our thumb pointing to the left, and then we see that our fingers curl up from the bottom and over the top. Okay, let's do another practice. So just next to that image, we see a north pole, but now it's moving away from the conductor. So if you were the coils, what you would sense or what you would feel is a change in flux where it is a north pole and it's getting weaker. It's receding. So based on Lenz's law, the purple magnetic field that gets induced is going to oppose that change. So it's going to want to stop that north pole from receding. Therefore, closest or on the left side of the coils will be a south pole, so that it would attract the receding north pole and try to keep it in its place. So another way that you can think about Lenz's law is that the induced magnetic field will always try to stop the change of whatever's happening to the original field. So if the original field is receding or moving away, then the induced magnetic field will always have a pole closest to the receding field that is opposite in poles to try to attract it and keep it close. And if the original magnetic field is approaching the coils, then the induced magnetic field will always have a like pole. Will always have a like pole facing the approaching field to try to repel it. So here we see a south pole on the left of the coils because it's going to try to stop that north pole from receding, which means on the other side of the coils we have a north pole. Now if we apply right hand rule again, we'll face our thumb towards the right and you'll see that your fingers curl up and over the top of the page and down towards the bottom. So these are good checkpoints right here, these kinds of practice problems, to see if we really understand all of the concepts that we've had thus far. A lot of what we're learning right now in electromagnetic induction is cerebral. They're very intellectual. So we want to make sure that we can take those concepts, digest them, and actually apply them to situations that could be happening. Now, we've talked a lot about electromotive force, or EMF. And so now we're actually going to break down what that really is and how it applies to us in this unit. So the reason that a magnetic field with a conductor nearby with a changing flux will result in an induced current is because, say we have a wire. Okay, so here in this picture we've got a long straight piece of wire, and it's traveling to the right. It's traveling to the right in this magnetic field that's drawn out of the page. Okay, so the magnetic field is coming out of the page. The wire is going to the right. And if we use right-hand rule number 2, which tells us the direction of magnetic force, you'll see that if you point your fingers out of the page and you point your thumb to the right, then your palm is going to face down the page. Now, your palm is the force that a positive charge will experience. So in this long straight piece of wire, the positive charges are going to feel a force down the page. Now, either by the back of your palm or by left-hand rule, whichever one resonates with you, you'll see that the negative charges experience a magnetic force up the page. So essentially, as this wire moves through the magnetic field, the magnetic force on the two different types of particles, positive and negative, are in opposite directions. And so it creates essentially a place of positive charge and a place of negative charge. And it just so happens that when that is the case, that wire will behave as if it's connected to a battery. So that highly concentrated difference in charge of positive and negative actually behaves like the positive and negative terminals of a battery. So that is how this idea of induced current comes to be when a magnetic field is changing and there is a conductor, like a wire, present. Now, the one formula that we had regarding EMF and how to calculate it was Faraday's law. So here we see EMF, electromotive force, and please do not get that confused with electromagnetic force. Okay, we don't have an acronym abbreviation for that. We just have an acronym for electromotive force. So EMF equals negative N times the rate of change of flux. The negative indicates to us Lenz's law, or represents Lenz's law, where the magnetic field that's induced will orient itself so that it opposes, right, opposite, opposes whatever the cause of the change in flux is. So we have a negative. We have a capital N for the number of coils of our conductor. So if there's only one coil, capital N would be 1. If it was 2 coils, capital N would be 2, and so on and so forth. And then we have multiplied by the change in flux over the change in time, or the rate of change of flux. Now remember, one of our definitions for flux was the number of field lines that intersect our cross-sectional area at a 90-degree angle. And so when we are calculating flux, we use cosine theta. We only use the component of the field lines. So if B is the field lines, we only use the component of the field lines that is indeed perpendicular to our cross-sectional area. Now, when the cross-sectional area is perpendicular to the magnetic field, it's perpendicular to the field, then that's when we'll get the largest induced EMF and current. Which makes sense, because when the field is perpendicular to the cross-sectional area, then we get the largest flux, and therefore the largest change in flux, which leads to the largest EMF and therefore the largest current. When the cross-sectional area is tilted, And now we see the case where we have a component of the field lines that would be perpendicular. A component of the field lines that would be perpendicular to the cross-sectional area. Then we would see that the induced EMF and current are smaller or are lesser than when the cross-sectional area is at 90 degrees. So we would be using a component of B, and that component that we use would be B cosine theta. So we'd use B cosine theta instead of B in all of our calculations. Now when the cross-sectional area, and I'm just going down the row, so I went from left to right, when the cross-sectional area is actually parallel to the field, okay, here we have the cross-sectional area parallel to the field, then the induced EMF and current are the smallest that they'll be, and they're actually 0. So when the loop is parallel to the magnetic field, we do not get an induced EMF and we do not have an induced current. And that should be relatively easy to remember because that's similar to our rules about charges moving in a magnetic field. Right? When a charge moves perpendicular to the field, the magnetic force is the greatest, and when a charge moves parallel to the field, there actually is no magnetic force, or the force would be 0. Now really quickly before we end, just a little bit of a discussion about EMF, potential difference, and current, because we've used those terms throughout this conversation, and I don't know if it's particularly clear that those three terms are in fact different. So EMF, electromotive force, refers to the voltage developed by an electrical source. Okay, it's the voltage developed by an electrical source. It's caused by converting from one form of energy into electrical energy. So when we go from mechanical energy into electrical energy, we talk about EMF as a result. And it's a little confusing because EMF is measured in volts. Okay, EMF is measured in volts, just like voltage and just like potential difference. So potential difference, or delta V, the change in V, refers to the observed difference in voltage between 2 points. Okay, between 2 particular points, and we usually talk about that across the battery. Okay, we've usually talked about that particular quantity of delta V as measured across the battery, the terminal voltage. This is also measured in volts. For current, I, current refers to the rate of flow of electric charges, and you guys know that it is measured in amperes, and an ampere is a coulomb per second, so it literally is the number of coulombs that pass through a cross-sectional area in a second. Now luckily for us, current is measured in amperes, and EMF is measured in volts, so we have a little bit of differentiation there, but unfortunately sometimes the terms EMF and current are used interchangeably, but there are in fact subtle differences between them, so I just want to reiterate that fact. Okay, so EMF refers to the voltage, not the current. It refers to the voltage developed from an electrical source. So the voltage developed per se in a circuit or in a conductor by an electrical source. And it is the result of converting one form of energy into electrical energy. Okay, thanks guys for tuning in. I hope that you feel a little more comfortable talking about electromagnetic induction and understanding what it all means. I'll see you guys next time on our Physics Fun channel.